Hello, Assalamualaikum.
Assalamu alaikum. Shahir, what is the update on homework? Did you try the latest worksheet?
Yeah, I'm halfway through the latest one. I did all
Very
the
good.
other ones.
So we can put a class. I will try to put an extra class on this weekend so we can discuss the queries. And the latest worksheet I have shared with you is with the solution. But now we should do, because our unit number 2 is there. Sorry, the topic number 2, second topic is in progress. So we need to do some work backup for query settling. Okay. Now we were
Okay.
in bonding, and in bonding, we were doing covalent bonding, right? We were doing bonding. In bonding, we were doing covalent bonding. In covalent bonding, we were discussing molecular orbital theory. This theory we had started last time. This theory says that orbitals combine, they overlap, and they form a molecular orbital. The greater the overlap, stronger the bond. This is called molecular orbital theory. So can you remind for me that what was our last writing? Can you check for me?
Yeah, last one was about oxygen double covalent bond and sp molecular orbit.
Acha. Okay, now give a new heading, sigma and pi bonds. It is an
Okay.
extension of the concept of covalent bond.
Done.
Now we are starting this article. Remember, this is a molecular orbital theory. Orbitals are s orbital, p orbital, d orbital, f orbital. And when two atoms bond together, these orbitals overlap. These are the three p orbitals. And you can identify these are the five d orbitals. Now you can see s orbital, p orbitals. So what about the molecular orbital theory? It says when a covalent bond is established, the valence atomic orbitals overlap to form a molecular orbital. And there are two types of overlaps. When orbitals overlap in this way, which is the maximum overlap, they get a sigma bond. And sigma bond is a strong bond. When orbitals overlap in maximum level and they overlap strongly, they get a sigma bond. Sigma bond is the first bond between two atoms. I just want to recall you that, for example, I take the example of oxygen. Okay, oxygen forms one, two, double bond. This is called double bond. Nitrogen forms one, two, three, triple bond.
Okay. Okay.
And hydrogen, one, single bond. So we have studied this in O-level chemistry, that some atoms are single covalent bonded, some atoms are double covalent bonded, and some atoms are triple covalent bonded. Obviously, triple bond will be very strong. Now, in A level, we make a concept that covalent bonds are of two types in molecular orbital weight. One is called sigma bond and second is called pi bond. Sigma bond is very strong. Pi bond is obtained by partial overlap. This is a weaker bond. This is the second bond. This is the third bond. So it means, let's say we are making nitrogen. The first bond is always sigma bond. The second bond is pi bond. The third bond is pi bond. Pi bond is weak. So there are two types of covalent bonding. One is called sigma bond and one is called pi bond. We have to copy this screen.
The left bond is a sigma bond, right? This one.
Yes, this is a symbol for sigma. And I write
Okay.
it for you here. This is a symbol and we call it sigma. And this is a famous math symbol and we read it pi. So let's repeat the concept. When two atoms bond together, their target is to attain noble gas configuration because it's a source of stability. This is the primary concept, okay? The second concept, when two atoms combine to make a bond, if they lose and gain electron, transfer of electron, an ionic bond is established. If they share electrons, a covalent bond is established. A covalent bond, the third concept, the covalent bond can be of two types: sigma bond, which appears when you have complete overlap, and a pi bond, which is of weaker cross link. So when you make the first bond between elements, it's a sigma bond. When you make the second bond, it is the pi bond. And remember that sigma bond is for complete overlap. And if you overlap like this, it is called a pi bond. Now you have to copy this screen. Let me know if you have copied it. Shahir, have you copied it?
Just finishing it. Okay, done. Yeah, done.
So this is called a pi bond. The sigma bond is much stronger compared to a pi bond. And when you talk about any structure in chemistry, whenever you talk about any structure in chemistry, it is coming from bonding. Bonding is the most important topic in my as a teacher. I emphasize that bonding is the most important chapter. Why? Because every explanation in chemistry comes from bonding. Even if you are doing any chapter, including the king of chapters, organic, even you're doing organic or you're doing any chapter, you always need bonding. So bonding is somewhere where every student should do maximum work. That is why I always give extra things in bonding, because bonding is where you can answer every question. So why a compound is not soluble in water, bonding has to be there. Why some compounds are easily traceable in our mass spectrometry, why there is a trend in ionic radius, why there is a trend in melting point, why there is a trend in boiling point. In all these topics, whenever you look for reason, whenever you look for a reason, you will get the answer from bonding. So bonding is actually the most critical, most critical topic in our chemistry. Now you look at this structure. This is methane. This is ethene, and it is reacting with bromine. The pi bond is weaker. It breaks and bromine two atoms attach on it. Pi bond, the double bond, is weaker. Now, this is our third concept for today. The primary bond is sigma bond. Sigma and pi are not important to remember, just like we remember some name. Chemistry is not worried about names. Bohr model, Rutherford model, Avba principle. You find them in books. Teachers also tell, I also use. Chemistry says the concept. Name of scientists are gradually phasing out. So sigma bond is the first bond between two atoms. It is like the vertebral column. It is like the backbone. It doesn't break. Pi bond is breakable. Now you have to copy this screen.
Yeah, done.
Okay, now right under it, pi bond is weaker.
Okay.
Pi bond is weaker. Now this is an example, a famous organic reaction where bromine water decolorizes, bromine water loses its color, and bromine gets into a compound. This compound is called ethene. It's an alkene. Now you have to copy this example. Write for example and then copy this screen.
Is called bromoethane, right?
Sorry.
This is called bromoethane.
It is called 1,2-dibromoethane. If you take it in A level, it is called 1,2
1,2-dibromoethane.
Dibromo.
But in this case, is the 1,2 necessary because there's
1,2 is
only two
numbering.
carbons? Yeah,
1,2
I know, but there's only two carbons anyways.
label it anywhere. It's a good thing if you copy that name also, 1,2-dibromoethane. And now the pi bond is delocalized. Pi electrons are delocalized and they can switch their positions. That is why pi electrons are easily capturable. Pi bond resonate like a string, which if you put some force and a guitar string vibrates. So pi bond is pi electrons are delocalized. They spread around the sigma bond and they can be easily attacked by external atoms. So now write under it that pi electrons are delocalized.
Yeah.
Pi electrons are delocalized.
A sigma covalent bond is formed by the overlapping of two s orbitals, or one s and one p orbital, or two p orbitals orientated along a common axis. A sigma covalent bond.
The simplest molecule we can discuss in terms of valence bond theory is the hydrogen molecule, H2. This molecule is formed by two hydrogen atoms sharing their 1s1 electron. When the atoms approach each other, their 1s atomic orbitals overlap. We can envisage some merging of the orbitals to form a common electron cloud containing two electrons of paired spins. Electron density in this cloud should be concentrated somewhere between the hydrogen atoms. The covalent bond formed by overlapping the two s orbitals is termed a sigma bond. Hydrogen atoms are linked by a sigma bond in the hydrogen molecule. The simplest
This is called electron density models. This is called, look at this, this is called electron density model. And they are hypothetical models and they are designed to make an idea. Look, this one, this is p orbital overlapping with p orbital. We call them electron density
oxygen
models.
atoms have 6 valence electrons. 2 of them are located in the 2s orbital, and 4 in the 3 2p orbitals. One of the 2p orbitals holds an electron pair, while the 2 others are occupied by single, unpaired electrons. 2 oxygen atoms can form one sigma bond by head-to-head overlapping of 2 2p orbitals. Notice that in this orientation, another pair of the 2 remaining 2p orbitals can overlap in a side-to-side manner. In this way, a second covalent bond is formed. This is a pi bond, since it results from the side-to-side overlapping of p orbitals. The oxygen atoms are bonded together by a double bond in the oxygen molecule. The double bond consists of one sigma bond and one pi bond. Oxygen atoms have 6 valence.
Now, types of covalent structures, you have to give a new heading, types of covalent structure.
Okay.
There are 2 types of structures in covalent. One is called simple molecules like bromine, like iodine, like chlorine. And there are macromolecular structures like diamond, graphite. So right under it, number 1, simple molecules. Like fluorine, chlorine, bromine.
Yeah, done. I wrote both. Okay.
Like
Yeah, I finished.
diamond, graphite,
Yeah, I finished. I said.
and SiO2. SiO2 is a very famous compound, even though it's present around us every time, but we do not normally follow it as a compound of that type. It is sand, and it is part of our life. Silicon dioxide. Silicon dioxide is a compound which is covering this name, and it is a very powerful compound. This is iodine. This is diamond. And this is diamond versus graphite. Now give a heading, shapes of molecules. This is a very challenging topic of IL chemistry. And you can say in bonding, within bonding, this topic is the most difficult. Shapes of molecules.
Okay.
Now, shapes of molecule actually comes with a first primary concept, which is called valence shell electron pair repulsion theory, VSEPR. You have to give this as side heading. valence shell electron pair repulsion theory is actually explaining the physics concept that electrons by nature repel each other, and electrons are present inside every bond. Every bond at least consists of two electrons. Bond is always consisting of two electrons. The shape adopted by a simple molecule or ion is that which keeps repulsive forces to a minimum. This is called VSEPR. You have to copy this screen now.
Copied it.
Now, this is called electron pair repulsion theory, VSEPR. Now, molecules contain covalent bonds, and bonds contain electrons, and physics says that electrons naturally repel each other. You can understand this concept only once you remember that bond is shown as a line, but within the bond there are at least two electrons. So bond is a negative rod. If this is a negative rod, it will surely repel other rods. So bonds always try to stretch out so that repulsion can be minimized. Look at this diagram closely. And then what will happen after a short time, the diagram spread out because the repulsion will move them apart. Now, why this structure is more stable? Because all bonds are equally spaced out, and now repulsion is minimum. All bonds are equally spaced out as far as possible to give minimum repulsive force. This is the core idea why molecules take a proper shape. Why molecules take a proper shape? Because bonds naturally repel each other. Now, repulsion between the bonds give rise to a concept of bond angle. Give an idea of bond angle. The presence of lone pairs on the central edge. Okay, fine. First, after giving the heading, write under it that every bond consists of electrons. Every bond consists of electrons. So bonds naturally repel each other. So bonds naturally repel each other.
Okay.
Due to this repulsion, continue writing in the same paragraph. Due to this repulsion,
Yep.
a molecule adopts a particular shape.
Yep.
With particular bond angle. With particular
Okay.
with a particular bond angle. Now, next line. For example, you have to copy this screen.
Okay, done.
Now, there is a concept of lone pair. Now, lone pairs are those pairs which are not used. Lone pairs are very repulsive in nature, extra repulsive in nature.
There are three types of repulsive interactions in molecules with lone pairs. They increase in the following order: bonding pair, bonding pair, bonding pair, non-bonding pair, non-bonding pair, non-bonding pair. There are three types of repulsive interactions in
Now, this is an important concept that you understood by now. The main idea is repulsion. The main idea is repulsion. And due to this repulsion, molecules adopt a particular shape. Lone pair repulsion is the maximum, while shared pair, lone shared pair repulsion is the minimum. Now you have to copy this concept.
For a shared pair to shared pair, the repulsion is low because of electron spin, is it?
This is not actually our A-level concern, but actually what happens when there is a lone pair cloud is bigger. It is called concept of electron density. Shared pair is like a much less aggressive pair because it is bonded. Lone pair is a bigger cloud. So lone pair is capable of producing more repulsion.
The Lewis structure of sulfur dioxide shows that sulfur forms two bonds to oxygen atoms, one single and one double. There is also one lone electron pair on the sulfur atom. Valence shell electron pair repulsion theory treats single and double bonds equally in terms of the repulsion between them. We can say that there are three groups of electron pairs on the sulfur atom. One group of two electron pairs representing a double bond, one electron pair in the single bond, and one lone electron pair. The mutual repulsion of these three groups positions them to point to the corners of a triangle. Since one of the corners is occupied by the lone electron pair, the molecule assumes the bent shape of a letter V. Since the repulsion between the lone and bonding pairs is stronger than the repulsion between two bonding electron pairs, the sulfur-oxygen bonds are pushed together to form an angle of less than 120 degrees. The Lewis structure of sulfur dioxide.
Now, look at this example. Sulfur dioxide, the molecule bends and take a shape of 120 degree, less than 120 degree. Now, when there is no lone pair, the angle reaches simply 120, which is called trigonal planar. Lone pair is more repulsive. Now, you have to copy these two examples.
Okay. 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 That's fine. We can take that as 130. I can redo.
You say
I
something,
can
sorry?
put that on the email. No, nothing. Okay, copy.
Now, there are some regular shapes. When we talk about normal shapes, a covalent bond will repel another covalent bond. And when you talk about some regular shape, I will inshallah try to post this for you for memory. There are some common shapes: linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. These are called some regular shapes. Now, beryllium chloride, take an example. BeCl2, this is the dot and cross Lewis structure. When you observe it, it has when you observe it here, you will observe that it has bond pairs too, and it has no lone pair. So there is no problem. Beryllium takes a regular shape, beryllium chloride. Now, beryllium chloride takes a straight shape because there is no lone pair.
Let us see how to predict the shape of a beryllium chloride molecule using the valence shell electron pair repulsion theory. The beryllium chloride molecule has only 4 valence electrons around the beryllium atom. These electrons are arranged in 2 pairs. According to the VSEPR theory, they repel each other and tend to position themselves as far apart as possible. They're located on opposite sides of the beryllium atom. Then the distance between the mutually repelling electron pairs is at a maximum. Consequently, the molecule assumes a linear shape, with an interbond angle of 180 degrees.
Now, see this one, adding another atom, and now presently it is 180. When I add another atom, you see the shape changes. This stretching is occurring, and now the bond angle becomes 120. You can look it again, so you will have a good concept. When it's a linear shape and you make the third bond like BeC or any element which has aluminum chloride like that, so now it reaches 120 degree. Now I'm talking about aluminum chloride, one of their favorite compounds, AlCl3. Now you look at this one, bond pairs are 3. There are 3 bond pairs. There are 3 bond pairs and no lone pair. So the angle becomes 120 degree. This is called trigonal planar. So give a heading, aluminum chloride. And just copy the circles I have made. Other things are not needed to copy.
Yeah, copied.
Look at this shape. Now I'm adding the fourth molecule. Look at this shape closely. A very, very important, a very challenging concept of chemistry. When you add the fourth particle, now the angle becomes 109.5 and it is called tetrahedral structure. Look it again. Now the fourth molecule, fourth particle is coming. So the molecule have to readjust it because they all have to spread out for maximum separation for minimum repulsion. Now the angle is 109. Methane is a famous example here. Methane, you know very well, methane is CH4. Now, in case of methane, look, there are 4 bond pairs. Methane means CH4. Okay. And now the shape. Now look at this style. It is called wedge. It is called dotted. Wedge means out of the page as a 3D model, and dotted means in the page in our model of 3D function. So remember to copy it like that, wedge and dotted. And you have to give heading methane. Copy only the circles. Let me know if you have copied it.
What's this triangle thing like for with the
Sorry.
hydrogen? When there's a bond with hydrogen, there's like this triangle thing. What's that?
No, there is no triangle thing. It's called wedge. You're talking about this one, right?
Yeah, that yeah.
It is called wedge. Wedge means out of the page. It's a 3D model, na? So they can't
Okay.
show it because in animation you can show. If you look at this animation, you will find it a 3D model. Look, this is a 3D model. So in 3D, the wedge means out of the page and dotted means in the page. Look, now you can look it again. Now you can see it clearly that how it actually is. This is called a 3D structure and it is tetrahedral.
Okay.
A carbon atom has 4 valence electrons. By sharing them with 4 hydrogen atoms, it forms 4 single covalent bonds. The resulting compound is called methane. In the methane molecule, the carbon atom achieves the stable configuration of neon, and each hydrogen atom achieves the stable configuration of helium. A carbon atom has 4
valence pairs of electrons are present in a methane molecule. In this case, minimum repulsion occurs with a tetrahedral arrangement of the bonds around the central carbon atom. A tetrahedron is a 4-sided pyramid having equilateral triangular faces. In methane molecules, each of the hydrogen atoms is located at one vertex of the tetrahedron. The interbond angle is 109.5 degrees.
Expansion of octet rule. Octet rule is a famous rule which says that when there are 8 electrons, in the outermost shell, the structure becomes stable. This is called octet rule. But many compounds in A level, many compounds defy this octet rule in A level. Now look at this nitrogen, 1s2, 2s2, 2p3. There are 3 unpaired. So you can make NCl3. NCl3 means 3 chlorine will come, the red downward arrows, no expansion in 2p orbital. But how you can make PCl5 in this model? How you can take 5 chlorine when you don't have space for that? This is where the expansion of octet rule comes, and it is called d orbital. This is called expansion of octet rule. It means that if you observe the last line, if you observe this one, okay, you can see 2 electrons here and 6 electrons here and 2. If you total them, 2 plus 6 plus 2, you will find 10 electrons. This is exceeding 8 electrons. So this is called expansion of octet rule, where an element can adopt more than 8 electrons. Now, for example, phosphorus 5 chloride. Now, phosphorus 5 chloride has 5 bond pairs. Angle is 120 and 90. This is the shape of the molecule. This is a special case. If you count 2 electrons, 2 electrons, 2 electrons, 2 electrons, 2 electrons, you will find the outer shell is containing 10 electrons, which is unusual. Similarly, sulfur 6 fluoride, it has bond pair 6, no lone pair, angle is 90. Again, you can count 2, 2, 2, 2, and 2. You can count them and you will find that there are 12 electrons, which is expansion of octet rule. You can look it here, you can look in the dot and cross diagram more easily that actually it is using the d orbital. D orbital details are not in our course, so I'm not going for this in writing, but you just have to remember that octet rule can be expanded. So give us side heading, expansion of octet rule. And then write sulfur 6 chloride. This is the name. And copy the circles.
Yeah, copied it down.
Now we are talking about some irregular shapes. Now give a heading, irregular shapes.
Okay.
Now irregular shape means that they actually define some rule. And this is the case when there is a lone pair. Lone pairs are always more repulsive in nature. Lone pairs always are able to give extra repulsion. Bond pair is less repulsive than lone pair, and which is less repulsive than lone pair, lone pair. It means repulsion is maximum between lone pair. As a result of extra repulsion, bond angles tend to be slightly less as the bonds are squeezed together. Now, for example, we talk about ammonia. Another famous example, ammonia is a gas at room temperature, and it has a lone pair on it has a lone pair on nitrogen. You have to copy this screen. Have you copied it?
Just copying it 1 second. Basically, a lone pair means that it's not connected to any
Yes, it
extra.
is not. It is not in the shared bond. It is not bonded with anyone.
Okay.
Now, when you make a molecule of ammonia, you will have a lone pair, and lone pair repulsion is much higher. That is why ammonia takes a special shape. All the bonds below are bent down. And now you have to copy this circle only. Other thing you can read, but copy the circle only. And I'm just coming, copy the circle. This is a 3D structure of ammonia. This is ammonia molecule in 3D. The top red-white balloon is the lone pair.
An example of a molecule with 4 valence electron groups around the central atom is the ammonia molecule. 3 electron pairs form bonds between the nitrogen and hydrogen atoms. There is also 1 lone pair on the nitrogen. In accordance with the VSEPR model, electron groups point towards the vertices of a tetrahedron. Since one vertex is occupied by a lone pair, the 4 atoms of the molecule take the shape of a pyramid. The interbond angles, equal to 107 degrees, are close to the tetrahedral angle of 109.5. The reduction of the angle arises from the stronger repulsive effect of the lone pair. An example of a molecule.
So, give a heading, water.
This has 2 lone pairs, right?
Yes.
Okay. Okay, done.
It has 2 lone pairs, and when you predict the shape of water, again you will notice that water has 2 lone pairs, and water in lone pairs are more repulsive. So now it has a special concept that water, look, this is the shape of water. It is called angular shape. Angle is 104.5. You have to copy this circle only.
Again, could I ask why is the wedge used? Is it just
Wedge means out of the page. In
out of
3D, in maths, in physics, wedge means that in the real sense, it is not in the page, it is out of the page.
okay?
It's only explainable when you see an animation. When it is actually 3D means 3 separate dimensions. 3D means 3 axes. Have you copied it?
Yes.
Okay, so we keep it up to here, and we will continue it inshallah in our next class. Okay, thank you.
Okay. Okay, that is.